When we're designing interlocking concrete block pavements, we're using DesignPave. When we're modeling rutting failure, we're using a different formula than what's used in Ostrodes. Ostrodes uses a fatigue formula which represents the way asphalt fails. We use Valkyrie and Edwards equation, which through the research that we've performed with University of South Australia is a more representative formula to determine the amount of allowable repetitions for a block paved system, okay? And that's really important to understand. So I just want to say it one more time that we don't use the fatigue formula in Ostrodes for asphalt. We use a different formula which was derived through the research that we did with University of South Australia, which is a more accurate representation of how block paved pavement systems rut. A paved system is a multi-layered, multi-modular system. And so what we do in the DesignPave software is we convert our multi-layered system into a homogeneous layer of subgrade type material. We use this formula, and I'm going to run through just a design example just to show you how that's applied. So here you can see that what we're doing is we're converting all pavement layers. So you've got a stiff, I'm going to call it a stiff block paved layer, concrete and jointing sand. You've got a softish bedding sand layer, then you've got a structural base course layer, and then a subgrade. So when we're looking at that system, we're extrapolating it out using Odomar into a single homogeneous layer of subgrade quality material, subgrade modulus material. We're then using Boussinesq's equation to determine our vertical and radial strain values at the subgrade. And what we're doing here is for an ESA, we're using a contact area of a contact radius of 0.15, which we can then use to determine area, and a tire pressure of 700 kPa. And so we've got our contact area and our pressure, and we can use that to determine the stresses at the subgrade. We've got stress at the subgrade. We've got a modulus now of subgrade quality material. So we can now determine our vertical strain value at the subgrade, and vertical strain being the deformation of the subgrade. So we're converting our sigma value into an epsilon z value, which is ultimately what the formula uses to determine repetitions, okay? And so what we've got here is we've got that Valkyrie formula rearranged to make the allowable repetitions the subject. And so depending on our strain value, keeping in mind as thickness increases, strain decreases, therefore the amount of repetitions essentially increase, we adjust our base thickness to ensure that we've got an allowable number of repetitions greater than our design value, okay? And that's what DesignPave is doing. It's adjusting the base thickness, which is the variable, in 5 mil increments to ensure that that equation is satisfied. And yeah, so providing that we're less than 1, the equation is satisfied, and we're trying to get as close to 1 as possible to ensure an optimal design. I'm just going to go through some of these formulas with a worked example before Keanu shows you just how that works. The other important thing to note is that the way block pavements behave, when we're putting sand in those joints, it actually, we use 10,000 ESAs before lockup occurs. And lockup is when we get full modulus out of our paver layer, let's just call it an 80 mil paver layer. So up until 10,000 ESAs, we're modeling, we're utilizing a modulus for our paver layer, similar to our base course modulus, so quite weak. So we're decreasing the overall thickness, which is increasing our strains, which is increasing our damage. And so we model the pavement both pre-lockup and post-lockup, determine the damage of both, and ensure that that value is less than our design ESA. And I'll show you how that works now. So we've got a design here, and in this design, I haven't nominated an ESA value. I've just put in a base course thickness of 190 mils just to show how it works. So we've got the way that DesignPave works. It's going to model both pavements, one with a paver modulus of 350, one with a paver modulus of 3,200, which is post-lockup. Where we get the 3,200 value for our pavers, it's defaulted into DesignPave. That came from Brian Shekel and the research that he did many years ago, which is still applicable today. And that's what ties into what we talked about earlier, the type of unit and the laying pattern. We can adjust the modulus of our paver layer accordingly. So if I look at this table here, a dentated unit, which is a type A unit, has a greater modulus than a rectangular unit, so 3,200 and 2,500 respectively. And that's where we can adjust our design to reflect the type of unit and the laying pattern that we're utilizing. So that's where the 3,200, the default 3,200 value comes from for the block pave layer. So here for our pre-lockup equivalent thickness using a modulus of 350, we get an equivalent thickness of 118, which translates into a overall thickness of 428 approximately. And when we compare that to our post-lockup equivalent thickness using a modulus of 3,200, we get 245 equivalent thickness and 555 respectively. So you can see by utilizing a higher modulus, we're getting an increased thickness in equivalent thickness, which again translates to lower strain values, higher repetitions. Here we've got I'm just doing post lockup for this presentation, but this same process is also done in parallel using the pre-lockup values. So using our equivalent thickness now of 555, we get a vertical strain value of -70 approximately, negative being a compressive force. Again, using our 555 thickness, our tire pressure of 700, and our Poisson's ratio, we get a radial stress of 1.18. They're subbed in to get a vertical strain value of 0.0014. Can you So that's how we've determined our vertical strain value. That is then put into the formula. So without doing the equations, we had a vertical strain value of 0.0022 for pre-lockup, and then 0.0014 for post-lockup. So you can see our allowable repetitions for both. And so we've got our first 10,000 ESA over our allowable, and then the remainder, and I've just used 100,000 ESAs in this example, just to show the values. So 10,000 over our allowable, 90,000 over our allowable gives us the damage factor, both pre and post lockup. The summation of those is less than 1, okay? What DesignPave would do in a practical sense, and Kiana will show this, is it will keep upping or reducing the base thickness to get a value as close as possible to 1, which gives us the most efficient design. So you can see here that we're well below. We could get around about 190,000 ESAs out of this 190 mil pavement thickness. DesignPave does that for you seamlessly. And I'm just going to talk about AADT and how that differs. So where we just use an ESA value there, a raw number, for example, 100,000. When we're doing an AADT design and we're using a traffic spectrum value, we're doing a pavement design or a damage factor, not for our ESA value, but for every axle group and axle load in our spectrum. So on average, we have around about 170 different configurations, so 5 group types and 34 load types. And we do that pre and post lockup. So if we're designing a pavement using an AADT method, whereas for the ESA value, it's doing 2, a pre and post. For an AADT traffic spectrum, it's doing 340 simultaneous damage factor calculations and optimizing the base thickness accordingly. And that's sort of what we're showing here. So given a million vehicle repetitions, single axle 10 kilonewton of 0.28 and a proportion of 0.393, we're getting 1,102 repetitions of that axle group type and axle load type. If we then work out how many for each group, how many for each load type, and do that pre and post lockup, that's how our design's working. So what that means in practical sense, if we're utilizing the traffic spectrum portion of DesignPave, we're doing a much more accurate design because we're truly representing how that pavement will be trafficked. So I'm just going to throw to Keanu, who will just go through DesignPave, and then we'll just finish off.
So to do this, I'm going to quickly go and recreate our ESA design example and just show you that what we've just shown you was transparent and exactly what you're going to get when you're working with DesignPave. So in our ESA design example, obviously we figured out the approximate amount of ESAs that we could manage, which was 100,000. And our subgrade CBR, we assumed the subgrade had a modulus of 50. In Ostroads, the subgrade CBR times 10 is the subgrade modulus. So we had a subgrade CBR of 5. Quickly calculating. And again, when we look at what Michael showed, it was quite an intuitive process. We were doing pre and post lockup, and we were going through several formulas. So while it's not overbearing in the case of an ESA, when I show you the AADT with 340 different combinations, it can be quite overbearing to do. So we have the option of choosing our base types. So base course of subgrade, base course subbase and subgrade, base course stabilized subbase and subgrade. We're just going to go for what we did in the example, which was a base course and a subgrade. So quickly checking our values, all of these are interchangeable. So if I'm using a 100 mil paver, I can use a 100 mil paver. If I'm using dentated or rectangular, I can use a 2500 value recommended by Shackle, or I can stake with 3200. Again, Poisson's ratio can be changed depending on what you know. Thickness of the sand, same story. And the base course. If I'm using a better quality base course material, I can use a 500 MPa and I can change my Poisson's ratio as well. So again, DesignPave is designed to be as simple and as intuitive as possible. So quickly designing it, we get 190 mil, which was exactly the same as what Michael showed in the example, right? If we can all see the graph. And if you wanted to extrapolate how DesignPave works, it's doing 5mm iterations each time. So if I press create a design chart, you'll have to bear with me. It's going to take a while because my computer's not the best. It's running about 1,400 simulations right now, and it's going to show you how that pavement will perform from 10,000 ESAs all the way up to 100 million ESAs. Okay, and it's doing that in 5mm increments. So if you had the ESA, you could pinpoint where on the graph, just like DesignPave, where on the graph your pavement will fail, or how, if you need to extrapolate it, you can create a thicker base to accommodate 100,000 ESAs. So right now it's just loading all the data. Sorry about this, guys. Perfect. So I won't press that button again because you just saw it takes a while. But again, see, we're seeing that curve. And if you actually look closely at the curve, you can see how it steps at 5mm increments. So it gives you a nice range, and you can use that to your advantage.